Hello, friend. Welcome to Science for Sleep. Tonight, we're going to talk about tree bark, what you might think of as nature's quiet jacket, the outer layer that wraps around every trunk, a kind of living coat shaped by time, weather, and growth. It may look rough or simple at first glance, but it is one of the most important parts of a tree's survival. Some trees grow bark so thick that it can survive a wildfire. In certain forests, the outer layer of a giant sequoia can grow more than a foot thick. That thickness is not decoration, it is insulation. When fire moves through dry grass and fallen branches, heat presses against the trunk, but the living tissue beneath remains protected. The outer bark chars slowly, the inside stays alive. If you enjoy these quiet journeys, you're welcome to subscribe, and if it feels natural, to leave a comment sharing where you're listening from tonight. It helps others find their way to this calm corner of the world, one sleepy traveler at a time. The quiet continues here, just as it is. Tree bark may look still and ordinary, but it is a layer built for survival. It resists flame, it slows heat, it protects against insects and fungi, and in some trees, it even sheds itself on purpose, peeling away in thin sheets like paper lifting from wood. What appears rough and silent is part of a long, steady process happening year after year. Bark is not simply the outer skin of a tree. It is made of multiple layers. The outermost layer is dead tissue. It no longer carries water or nutrients. Beneath that, there is inner bark, which is alive. The inner bark helps move sugars made in the leaves down into the trunk and roots. That movement is essential. Without it, the tree cannot feed itself. Between the wood and the bark sits a thin living layer called the cambium. The cambium is only a few cells thick, yet it produces new growth each year. It creates new wood inward and new bark outward. As the tree grows wider, older bark moves outward and becomes the protective shield we can see and touch. When bark grows thick, it forms cracks and ridges. These patterns are not random. They form as the trunk expands. The outer bark cannot stretch forever, so it splits. Some species form deep furrows. Others stay smooth for decades. Birch trees peel in white layers. Sycamores shed in patches of pale green and cream. These changes are part of the tree's rhythm. Even something as familiar as cinnamon is bark. The spice comes from the inner bark of certain tropical trees. When harvested and dried, it curls into the small brown rolls found in kitchens around the world. What smells warm and sweet once carried nutrients inside a living trunk. Bark protects against more than fire. It slows the loss of water. It shields delicate cells from freezing air. It reduces damage from sunlight. Thick bark absorbs impact from falling branches or passing animals. In many species, sticky resin flows into small wounds, sealing them before insects can enter. If bark is removed completely around the trunk, the tree cannot survive. This is called girdling. Without its inner bark, sugars cannot move from leaves to roots. The living system beneath the surface depends on that thin, quiet layer. A tree does not move away from danger. It cannot step aside when heat rises or wind pushes hard. Its protection must be built in. And that protection builds slowly, a little thicker each year, a little stronger with time. As we begin this quiet exploration, you can picture bark not as something dry or lifeless, but as a layered shield, a surface shaped by weather, sunlight, and growth, a boundary that absorbs the world so that life inside can continue. When you look at a tree, it is easy to think of bark as a single outer shell. But bark is not just one layer. It is a collection of layers, each with its own role, each forming slowly as the tree grows outward. What we casually call bark includes everything outside the wood that carries water upward. It is not separate from the tree's life. It is part of it. Just beneath the rough surface is the inner bark, also known as the phloem. The phloem has a quiet but essential job. It carries sugars made in the leaves down into the trunk and roots. During the day, leaves use sunlight to make energy through photosynthesis. That energy is turned into sugars. Those sugars must travel downward to feed the rest of the tree. The phloem is the pathway that allows this movement. Outside of the phloem sits the outer bark. The outer bark is made mostly of dead cells. These cells no longer carry nutrients. They no longer grow, but they serve as a shield. Over time, as new layers form beneath them, the older layers are pushed outward. They dry, thicken, crack, and sometimes peel away. This slow outward movement is constant. Each growing season, the thin cambium layer beneath the bark produces new cells. Some become new wood, called xylem, which carries water upward from the roots. Others become new phloem, which carries sugars downward. The bark we see today was once living tissue closer to the center of the tree. You can picture it as a steady outward drift. The trunk expands a little each year. The inner layers remain alive and active. The outer layers gradually become protective casing. If the phloem layer is interrupted all the way around the trunk, the tree cannot survive. This is called girdling. Without the phloem, sugars made in the leaves cannot reach the roots. The roots begin to starve. Even though water may still move upward through the xylem, the balance is broken. The living system beneath the bark depends on that thin transport layer remaining intact. The outer bark protects this delicate movement. It reduces water loss by limiting evaporation. It blocks many insects from reaching the softer tissue beneath. It shields against fungal spores that drift in the air. It absorbs minor impacts from wind-blown debris or passing animals. Some bark is thin and smooth when a tree is young. As the trunk widens, tension builds in the outer layer. Because the outer bark cannot stretch forever, it begins to split. The patterns that form are shaped by species and growth rate. Fast-growing trees often develop deep ridges. Slow-growing species may remain smoother for decades. The texture you see on an oak or pine is not random decoration. It is the visible result of internal growth pushing outward year after year. If you were to gently press your hand against a tree trunk, you would be touching cells that may have formed many seasons ago. Beneath your palm, closer to the center, are older layers of wood. Just under the bark, the cambium continues its quiet work, thin, flexible, always producing new growth. Bark is not static. Even when it appears still, it is part of a living process. It forms from within. It shifts outward. It protects what remains active beneath. The surface may feel dry and rough, but beneath that surface, movement continues in narrow channels, carrying energy downward and water upward. A steady exchange happening quietly, season after season. The next time you notice the texture of bark, you might picture more than a surface. You might imagine layers stacked over time, living tissue beneath protective casing, a system moving slowly outward, always adding, always adjusting, even when nothing seems to change. Just beneath the bark, hidden from view, there is a thin living layer that quietly keeps the tree growing wider each year. This layer is called the cambium. It is not thick. In most trees, it is only a few cells deep. You could pass by it without noticing. And yet, this narrow ring of tissue wraps all the way around the trunk, forming a complete circle. It is responsible for nearly all outward growth. Without it, the tree would no longer become wider. It would simply remain the same size, season after season. The cambium sits between two important systems. On the inside is the xylem, the wood that carries water from the roots up toward the leaves. On the outside is the phloem, the inner bark that carries sugars made in the leaves down toward the roots. The cambium creates both of these tissues. It produces new xylem inward and new phloem outward. You can imagine it as a slow-moving ring, dividing and adding cells in both directions. On one side, it strengthens the trunk with new wood. On the other side, it builds new inner bark that will one day become part of the outer protective layer. Each growing season, when temperatures rise and moisture becomes available, the cambium becomes active. Its cells divide more quickly in spring. During this time, it produces larger xylem cells. These cells appear lighter in color when the wood is cut. As summer continues and growth slows, the cambium forms smaller, denser cells. These appear darker. The contrast between the lighter spring wood and the darker late summer wood forms a ring. Each ring represents 1 year of growth. If you have ever looked at a tree stump and counted the rings, you are observing the history created by the cambium. Wide rings often suggest years with good rainfall and sunlight. Narrow rings may reflect drought, cold, or stress. The tree records its experience in wood, one thin layer at a time. But the cambium itself always remains just beneath the bark, moving outward as it builds. The wood inside grows older. The bark outside thickens. The cambium stays between them, creating new boundaries each year. If this thin ring is damaged in a small area, the tree can often repair itself by growing around the injury. It forms what is called callus tissue, slowly sealing over the wound. But if the cambium is destroyed in a complete circle around the trunk, the tree cannot survive. This process, known as girdling, interrupts the flow of sugars through the phloem. The roots are cut off from their energy source. Even though water may still move upward through the xylem for a time, the balance cannot continue. The life of the tree depends on that narrow band remaining unbroken. The cambium also responds to its surroundings. In years with steady rain and warm sunlight, it produces more cells. In dry or cold years, it slows down. The pace of division changes, but the pattern remains steady. It divides, it adds, it moves outward. When you place your hand on a tree trunk, you are touching layers that were once formed by this living ring. The bark beneath your fingers may have started as soft inner phloem many years ago. Over time, as new layers formed beneath it, that tissue was pushed outward. It hardened, it dried, it became protective outer bark. The cambium never becomes outer bark itself. It always remains just inside the newest layer of wood and just inside the newest inner bark. It continues its work quietly, never thickening into a visible band. Unlike branches, which grow longer at their tips, the trunk grows wider from this circular layer. The tree does not stretch its surface outward like fabric. Instead, it builds new layers beneath, slowly expanding the trunk from within. Picture the trunk widening by just a small fraction each year. The change is almost invisible from one season to the next. But over decades, the difference becomes clear. A slender sapling becomes a sturdy trunk. A smooth surface develops furrows and ridges as outer bark struggles to keep up with the steady expansion underneath. The cambium is the source of that steady outward push. Even in trees that survive wildfire, even in those with bark thick enough to resist heat, the cambium must remain alive for the tree to continue. The outer bark may char and darken. The surface may crack and scar. But as long as the cambium beneath remains intact, new growth will continue. It is easy to overlook something so thin. But this narrow ring shapes the size, strength, and structure of the tree. Every layer of bark you see, every growth ring hidden inside the trunk, every widening year, all of it begins with a few cells dividing quietly in a circle. No noise, no sudden change, just steady outward growth, built layer by layer over time. As a tree grows wider, its outer surface faces a quiet problem. The trunk expands each year, pushed outward by new layers forming beneath. But the outer bark cannot stretch forever. It is made mostly of dead cells. It does not divide or grow the way the cambium does. So as the trunk slowly increases in width, tension begins to build across the surface. Eventually, that tension must release. That is why bark cracks. The deep furrows on an old oak, the long ridges on a pine, the rough plates that lift slightly at the edges. These are not random decorations. They are the visible result of steady outward growth pressing against a layer that cannot expand smoothly. Each growing season adds a thin band of wood beneath the bark. The cambium pushes outward. The inner bark forms. The outer bark, already dry and rigid, begins to strain. Over time, small fractures appear. These fractures widen into grooves. The grooves deepen as the trunk continues to thicken. In some species, the cracks form long vertical ridges. In others, they create block-like plates. Some trees produce diamond-shaped patterns. Others form twisting spirals. The pattern depends on how the cells in the outer bark were originally arranged and how the trunk expands over time. Fast-growing trees often develop deeper fissures because growth pressure builds more quickly. Slower-growing trees may remain smoother for longer periods. Young trees of many species have relatively smooth bark. As they age and widen, texture increases. You can picture the surface as a slowly drying layer over something that continues to move beneath it. The outer bark, also called the rhytodome, is made of protective dead tissue. It forms when older phloem cells are pushed outward and gradually die. These cells become thickened with substances like suberin, which makes them resistant to water and decay. Suberin is a waxy material that helps reduce moisture loss and blocks pathogens. But once these cells are fully dead and hardened, they no longer adjust easily. They cannot stretch like living tissue. So as the trunk expands, the hardened outer bark fractures. These fractures are not harmful. In fact, they are part of the design. The cracks allow older bark to loosen and sometimes shed. In some species, this shedding happens in flakes or strips. In others, the bark remains attached but forms deep channels. These grooves can provide shelter for insects and small organisms. They can collect moisture after rain. They can even influence how sound moves along the trunk. The depth of bark cracks often increases with age. An older tree may have furrows deep enough to rest your fingers inside. Those ridges reflect decades of outward pressure from the cambium beneath. Temperature can also play a role. In very cold weather, outer bark may contract slightly. In warm conditions, it expands a bit. Over many cycles of heating and cooling, small stresses add to the larger growth pressures. The surface responds slowly, forming patterns that remain long after the weather changes. Sunlight influences bark as well. In some species, darker bark absorbs more heat, which can speed growth on one side of the trunk. This can lead to subtle differences in thickness and cracking. On slopes, trees may grow unevenly due to gravity and wind, affecting how tension builds across the surface. If you run your hand along a ridged trunk, you are feeling the outcome of these slow forces. Years of expansion. Layers pushing outward. Dry tissue separating along natural lines of weakness. Each crack marks a place where growth demanded space. And yet, beneath those cracks, life continues in narrow, active layers. The cambium remains flexible. The phloem still moves sugars. The xylem still carries water upward. The surface may look rough and broken, but the interior remains steady and organized. Even fire interacts with cracked bark differently than with smooth bark. Deep furrows can sometimes trap embers, but thick ridges also provide insulation. The outermost charred layers may fall away, revealing intact tissue beneath. The pattern of cracks influences how heat travels across the trunk. Over time, the cracks themselves become part of the tree's identity. They help foresters identify species from a distance. They help ecologists estimate age. They shape how moss or lichen attaches to the surface. Nothing about the cracking is rushed. It does not happen in a single season. It develops gradually, responding to pressure that builds year after year. You can imagine the trunk widening quietly from within, the outer bark holding as long as it can, then slowly, gently, separating along lines that relieve the tension. What looks like damage is simply adjustment. The surface yields just enough to allow continued growth beneath, and in that yielding, texture forms. A record of steady outward expansion, written in ridges and grooves that remain long after the season that created them has passed. Some trees do not wait for deep cracks to form. Instead of holding their outer layers for decades, they let them go. If you have ever seen a birch tree with thin white sheets curling away from its trunk, or a sycamore with patches of pale green and tan peeling back like pieces of old paint, you have seen bark that sheds on purpose. This shedding is not a flaw. It is part of how those species manage their outer surface. As a tree grows outward, older bark is pushed farther from the living center. In many trees, that bark hardens, thickens, and splits into ridges. But in peeling species, the outer layers loosen and separate in thin sheets or plates. This happens because the outer bark forms in layers that do not bond tightly together. As the trunk expands and new tissue forms beneath, the older surface layers detach more easily. Wind, rain, and simple gravity help lift them away. The result is a trunk that appears to renew itself. In paper birch, the outer bark contains high amounts of oils and a substance called betulin. Betulin gives the bark its pale white color. It also makes the bark somewhat water resistant. As the tree widens, thin horizontal layers peel off in papery strips. Beneath them, fresh white bark is revealed. This peeling may help remove fungi or small organisms that attempt to settle on the surface. By shedding old layers, the tree reduces long-term buildup of parasites and lichen. The surface stays relatively clean compared to deeply furrowed bark. Sycamores shed in a different pattern. Instead of thin strips, they lose bark in larger patches. This creates a mottled appearance, with areas of grey, cream, and green. As the outermost layer loosens and falls away, smoother inner bark becomes visible for a time. The peeling also changes how sunlight interacts with the trunk. Lighter surfaces reflect more light, which can reduce heat buildup in strong sun. In some climates, this may help regulate temperature along the trunk surface. Eucalyptus trees are well known for dramatic shedding. In certain species, long ribbons of bark hang loosely before falling away. The shedding process can be so regular that the ground beneath these trees is often scattered with curled strips. Unlike cracking, which forms grooves that remain for decades, peeling removes old tissue entirely. The surface becomes smooth again, at least for a while. Over time, the cycle repeats. This shedding does not expose the delicate cambium. Beneath the peeling layer, there is still protective tissue. The living layers remain safe. What falls away is bark that has already served its purpose. You can picture it as a slow release. As new bark forms beneath, the outermost layers are no longer needed. They dry, they separate, they drift down. In climates with high humidity, peeling may also help reduce the weight of moss or fungal growth. A smooth surface makes it harder for some organisms to attach deeply, though moss and lichen still grow on peeling trees. The constant renewal prevents heavy buildup over long periods. Not all trees peel dramatically. Some shed in very fine flakes that are barely noticeable. Others lose bark in irregular plates that add to their texture. The pattern depends on species, growth rate, and environmental conditions. Temperature changes may influence peeling as well. Repeated warming and cooling can weaken bonds between bark layers. As the trunk expands slightly in warmer weather and contracts in cooler air, small separations can grow larger. When you see bark lifting gently from a trunk, you are watching the result of years of outward growth. The tree does not actively push the bark off. It simply continues to grow beneath it. The outer layer reaches a point where it can no longer remain attached, and so it lets go. What remains is a fresh surface formed quietly beneath, ready to face wind, rain, sunlight, and passing seasons. Peeling bark can feel delicate to the touch, thin and papery, or firm and curling. Beneath your fingers, there is a sense of renewal, a surface that has been recently revealed, though the process that created it took many years. Even in still air, shedding continues slowly. Small flakes loosen, larger sheets separate. The tree remains rooted and steady, but its outer covering changes. It is a different strategy from thick armor or deep cracking. Instead of building layers that last for decades, these trees renew their surface again and again. And in that renewal, the trunk appears lighter, smoother, almost refreshed, though the slow work beneath remains the same. If you imagine a tree standing through wind, rain, cold nights, and passing heat, bark begins to feel less like a surface and more like armor. Not metal, not rigid plating, but a layered shield built slowly over time. Bark protects the living systems inside the trunk in several quiet ways. It does not block every threat. It does not make the tree invincible, but it reduces damage, slows intrusion, and absorbs stress before it can reach the delicate layers beneath. One of its main roles is protection against insects. Many insects search for soft entry points into wood. Beetles, borers, and larvae often try to reach the cambium or the nutrient-rich phloem. Thick outer bark makes that task more difficult. Deep ridges and hardened surfaces create physical barriers. Some bark contains chemicals that deter insects. In pine trees, resin canals run through the bark and wood. When the surface is damaged, sticky resin flows outward. This resin can trap insects and block further entry. The flow is slow but effective. A small puncture may fill with sap within minutes. Over time, the hardened resin forms a seal. Bark also shields against fungal infection. Fungal spores drift through the air constantly. When they land on exposed tissue, they may attempt to grow inward. Outer bark, especially when thick and corky, acts as a barrier. It reduces the chance that spores will reach the living phloem beneath. Some species contain natural compounds in their bark that resist fungal growth. These compounds make it harder for decay to spread quickly. If bark is cracked deeply, fungi may enter. But even then, the tree has additional defenses. The first line of resistance is always the outer surface. Moisture control is another important function. Trees lose water through their leaves during the day. This process is necessary for nutrient movement and cooling. But water loss through the trunk would be wasteful. The outer bark contains substances like suberin that make it water resistant. This reduces evaporation directly from the trunk. In dry climates, this protection becomes especially important. Thick bark slows the rate at which internal moisture escapes. The surface may feel dry and rough, but that dryness helps conserve water inside. Heat is another force bark must manage. When sunlight strikes a trunk, energy transfers into the outer layers. Thick bark slows this transfer. It acts like insulation on a building. The deeper tissues warm more slowly. In winter, this insulation also slows heat loss from inside the tree during freezing nights. In species like the giant sequoia, bark can exceed 12 inches in thickness. That thickness is not accidental. It slows heat penetration during wildfire. Flames may scorch the outside. The interior remains protected long enough for the fire to pass. The structure of bark matters here. Fibrous bark traps small pockets of air. Air is a poor conductor of heat. trapped air within the bark, the better it can resist rapid temperature changes. When minor injuries occur, bark works together with internal systems to seal damage. If a small branch breaks or an animal scratches the trunk, resin or sap may flow to the surface. In conifers, resin is especially important. It fills the wound, hardens, and blocks entry points. In other species, callus tissue begins forming along the edges of the injury. The outer bark may not close over the wound immediately, but it helps protect the exposed area, while the tree responds from within. Bark does not move. It does not contract like muscle, but it absorbs impact. It reduces the force of wind-driven debris. It softens the effect of temperature swings. It slows invasion. You can picture the trunk standing in shifting weather, heat pressing against it, insects crawling across its surface, rain running down its grooves. Beneath that textured layer, the cambium continues dividing quietly. The armor is not perfect. Some injuries still occur. Some insects succeed. Some fungi enter. But without bark, the tree would be exposed. Every ridge, plate, and fibrous strip contributes to that protection. Layer over layer, built from within, forming a shield that allows the life beneath to continue its slow outward growth. And when that armor is breached, the tree does not panic. It does not repair itself the way skin does. It responds in its own way. It grows around what has happened. When a tree is wounded, it does not heal the way skin does. There is no closing of the surface in the same way. No knitting of tissue back together. Instead, the tree responds by growing around the injury. If bark is cut or torn, the exposed area does not simply seal shut. The damaged wood remains in place. What changes is the growth that forms at the edges. The cambium, still alive around the wound, begins producing new cells that slowly curve inward from the sides. Over time, these layers expand and attempt to cover the exposed area. This process is called compartmentalization. Rather than repairing damaged tissue, the tree isolates it. It builds boundaries around the injured region. Specialized cells form walls that limit the spread of decay. These internal walls slow the movement of fungi or bacteria through the wood. The damaged section may remain inside the trunk for decades, but it is sealed off from healthy tissue. You can picture the trunk as a series of layers, each one laid down year after year. When injury occurs, new layers form around the wound's edges. They do not erase what happened. They grow in response to it. If a branch breaks during a storm, the tree begins to form what is called wound wood. This wood grows in a circular pattern around the break. Slowly, the open area becomes smaller as new tissue builds over it. The shape of the scar reflects the original injury. A wide break leaves a broad mark. A narrow cut leaves a thin line. Fire scars are among the most visible examples of this process. When wildfire passes through a forest, flames may burn one side of a trunk. The outer bark may char and fall away. If the cambium beneath survives, growth continues on the unburned side. Over time, new layers form around the damaged area. The scar remains visible as a darkened vertical strip or hollowed section. In some trees, repeated fires leave layered scars within the wood. If the tree is later cut, those scars can be counted. Each burn leaves a record, preserved inside the rings. Lightning leaves a different kind of mark. When lightning strikes a tree, electricity travels down the trunk toward the ground. The intense heat can vaporize moisture inside the wood, causing bark to split suddenly. Long vertical cracks may appear. Sometimes entire strips of bark are blown outward. The trunk may survive if the cambium is not destroyed all the way around. Even years later, the path of the strike can often be traced as a vertical scar running from canopy to root. Animals can leave scars as well. Deer rubbing antlers against young trunks may strip bark in patches. Bears climbing can leave claw marks. Insects may bore entry holes. Each of these marks becomes part of the tree's visible history. Unlike skin, which attempts to close seamlessly, bark carries memory outward. The scar does not disappear. It becomes surrounded by growth. The edges thicken. The shape remains. This slow response is steady. It may take many years for wound wood to cover a large break. In older trees, scars may remain open for decades. The tree continues to function, drawing water upward and sugars downward, even while carrying these visible marks. The presence of a scar does not always mean weakness. In many cases, the internal compartmentalization prevents decay from spreading. The tree sacrifices a small section to preserve the whole. You can imagine the trunk standing through seasons after an injury. Rain falling into a hollowed scar. Sunlight warming one side more than the other. The cambium, still active along the edges, adding thin layers each year. Time becomes visible in those curves. If you run your fingers along a scarred section, you might feel raised ridges where new tissue formed. You might notice how the bark dips inward where damage once occurred. These textures are records of response. Nothing about the process is rushed. The tree does not erase what happened. It adapts around it. It builds new layers that incorporate the past into its structure. In forests where fire is common, many trunks carry these darkened marks. In areas prone to storms, broken branch scars may appear in patterns along the bark. Each mark reflects a moment, and as growth continues, those moments become part of the tree's outward surface. Visible reminders that survival is not about avoiding all damage, but about responding slowly and steadily when it arrives. Over time, the scars remain, softened by new growth, yet still present. A surface shaped not only by protection, but by response. In some forests, fire is not an accident. It is part of the cycle. And in those forests, certain trees have bark built to endure it. Giant sequoias are among the most well-known examples. Their bark can grow more than 12 inches thick. If you were to stand beside one and press your hand against its trunk, you would be touching a fibrous outer layer that feels almost spongy. That thickness is not solid wood. It is layered, cork-like tissue filled with air pockets. Those air pockets slow the transfer of heat. When wildfire moves across the forest floor, flames may lick against the trunk. The outer surface may blacken, but heat travels slowly through thick bark. By the time it reaches the delicate cambium beneath, the fire may already have passed. This insulation is one reason sequoias can live for thousands of years. Other species use similar strategies. Ponderosa pines develop thick, plated bark as they mature. The bark becomes deeply furrowed, with large ridges that resist heat penetration. Young trees are more vulnerable, but as they age, their bark thickens and their resistance increases. The texture matters as much as the thickness. Fibrous bark traps air. Corky bark resists flame. Deep ridges break up the path of heat. Each of these structural traits slows the movement of energy from the outside inward. Fire in many ecosystems clears dry brush and fallen branches from the forest floor. Without periodic fire, debris can accumulate. When a blaze does occur after long suppression, it may burn hotter and longer. But in forests where low-intensity fires happen regularly, flames stay closer to the ground. Thick bark trees are adapted to survive these lower flames. Some species even depend on fire for reproduction. Certain pine cones are sealed with resin that melts only at high temperatures. These cones remain closed for years, sometimes decades, holding seeds inside. When fire passes through, heat melts the resin. The cones open. Seeds fall onto soil cleared of competition and enriched with ash. Without fire, those seeds might never be released. In this way, bark becomes part of a larger survival pattern. It protects the tree long enough for the cycle to continue. Flames remove undergrowth. Heat triggers seed release. New saplings grow in the open light. Even so, bark is not immune to damage. In intense wildfires, outer layers may be charred deeply. In some cases, bark can crack under rapid heating. If flames burn long enough to destroy the cambium in a complete circle around the trunk, the tree will not survive. But in many natural fire regimes, thick bark provides enough protection for recovery. You can picture the trunk standing as flames move past, the outermost surface darkening, the fibrous layers absorbing heat. Beneath that, the cambium remains intact. Water continues to rise through the xylem. Sugars continue to move through the phloem. After the fire, blackened bark may remain for years. Scars may form where heat was strongest. But growth continues. Some trees show multiple fire scars along one side of the trunk. Each scar marks a separate event. Inside the wood, those years are recorded in growth rings. The ability to survive fire depends partly on age. Young trees with thin bark are more vulnerable. As the tree grows and bark thickens, resistance improves. The outward expansion driven by the cambium builds protection over time. Cork oak trees offer another example. Their bark is thick and corky, filled with suberin. This substance resists heat and water. Even after bark is harvested for cork production, the tree grows a new layer. That new bark retains the same fire-resistant properties. In regions with seasonal drought, where lightning strikes are common, these traits are not accidental. They are shaped by climate and history. Fire-resistant bark does not eliminate fire. It allows survival through it. You might imagine a quiet forest after flames have passed. The ground is cleared. Ash settles. Some trunks are darkened but standing. Above, branches still hold green needles or leaves. Beneath the bark, life continues. The protection is not dramatic. It is not visible in motion. It is built slowly, year by year, until the trunk can withstand heat long enough to endure. And because bark slows the movement of heat, it becomes not just a shield, but a bridge between destruction and renewal. The surface may burn, but the layers beneath remain alive. And from that survival, the cycle begins again. Fire is one kind of heat, but trees face temperature shifts every day, in every season. From cold winter nights to bright summer afternoons, the trunk absorbs and releases warmth slowly. And much of that regulation depends on bark. Bark acts as insulation. In winter, when air temperatures drop below freezing, the living tissues inside the trunk are vulnerable. Water inside cells can freeze. Ice crystals can damage delicate structures. But thick bark slows the loss of heat from the inner wood. It reduces how quickly cold air penetrates toward the cambium. This slowing matters. If temperature changes happen gradually, cells have time to adjust. Sudden drops are more dangerous than steady cold. Bark buffers these shifts. It reduces the speed at which internal temperatures follow the air outside. In summer, the opposite challenge appears. Sunlight strikes the trunk, especially on the south-facing side in the northern hemisphere. Dark bark absorbs solar radiation more readily than light bark. As the outer surface warms, heat begins to move inward. Again, bark slows that transfer. The thickness and structure of bark influence how much heat reaches the living layers beneath. Dark-colored bark tends to absorb more heat. This can be helpful in colder climates, where additional warmth may support growth during short seasons. But in very hot regions, excessive heat can damage cells. In those places, some trees develop lighter bark that reflects more sunlight. Birch trees, with their pale outer layers, reflect a significant amount of light. The white surface reduces heat absorption. In contrast, many conifers have darker bark that warms more quickly. Texture also plays a role. Deep furrows create small pockets of shade. Ridges cast shadows across grooves. This uneven surface reduces uniform heating. Air can circulate within the cracks, helping disperse warmth. Smooth bark, by comparison, may heat more evenly across its surface. Temperature swings during late winter and early spring can be especially stressful. On bright days, the south side of a trunk may warm significantly while the north side remains cold. When temperatures drop quickly after sunset, the rapid cooling can cause frost cracks. These cracks often appear as long vertical splits. They occur when outer layers cool and contract more quickly than the wood inside. Bark thickness influences how severe these cracks become. Thicker bark provides more insulation, reducing the sudden shift. In very cold climates, some species maintain thinner bark, but rely on other adaptations, such as antifreeze-like compounds within their cells. In milder climates, thicker bark can afford additional protection without the same metabolic cost. Moisture content affects temperature regulation as well. Bark with higher water content can absorb heat differently than dry bark. Substances like suberin make outer bark water resistant, limiting how much moisture moves in and out. This contributes to stable internal conditions. You can imagine the trunk standing through a winter night. Cold air settles. Frost forms on the surface. Beneath that surface, layers of bark slow the chill. The cambium remains protected from rapid freezing. Then morning light returns. The outer bark warms first. Heat moves inward gradually. The process is steady, not abrupt. In hot climates, midday sun presses against the trunk. The outer bark absorbs or reflects energy depending on its color and thickness. The living layers beneath respond slowly, shielded from sudden spikes. Over time, climate shapes bark form. Trees in regions with frequent temperature extremes often develop thicker or more insulating bark. Those in stable, moderate environments may remain smoother and thinner. These patterns are not random. They reflect long-term adaptation. The bark becomes a mediator between atmosphere and interior. When wind blows across the trunk, it removes some surface heat. When rain falls, it cools the bark quickly. Yet beneath, the cambium continues its work in relatively stable conditions. Temperature regulation is not dramatic. It is not visible in motion, but it influences survival every day. Each ridge, each fibrous layer, each cork-like cell contributes to slowing the exchange between inside and outside. The trunk stands exposed to weather. The bark stands between. And in that quiet space between air and living tissue, heat moves slowly, buffered, moderated, softened, allowing growth to continue through cold nights and bright days alike. Not all bark faces the same conditions. A tree rooted in desert sand lives a different temperature story than one growing near the edge of Arctic tundra. A trunk standing high on a mountain slope experiences wind and sun differently than one in a sheltered valley. Climate shapes bark over time, pressing slowly against the outer layers and favoring forms that endure. In desert regions, sunlight is intense. Air is dry. Rain may be rare for months at a time. Bark in these conditions must reduce water loss and manage strong solar exposure. Some desert trees develop thick, light-colored bark that reflects heat. Others grow bark with deep cracks that allow air to move across the surface, cooling it slightly. The Palo Verde tree offers one example. Its bark is green and contains chlorophyll, allowing it to carry out photosynthesis even when leaves are shed during drought. This green bark reduces reliance on foliage and helps conserve water. The outer surface is smooth but tough, adapted to resist dryness and intense sun. Mesquite trees grow bark that is rough and furrowed. The texture provides some shading across the trunk and protects against heat stress. Thick outer layers help reduce moisture evaporation from the inner tissues. In extremely hot climates, thinner bark might allow heat to move inward too quickly. So over generations, trees that survived developed bark that slowed that transfer just enough. Arctic and subarctic trees face different challenges. In northern forests, growing seasons are short. Temperatures can remain below freezing for long stretches. Trees such as black spruce or birch may have relatively thin bark compared to fire-adapted species, but they rely on internal antifreeze-like compounds in their cells to resist freezing. The bark in cold climates still slows rapid temperature shifts, but excessive thickness may not be necessary where fire is less common and sunlight is weaker. High-altitude trees experience strong wind and intense ultraviolet radiation. On mountain slopes, bark may develop thicker protective layers to guard against wind-driven ice particles and sudden weather changes. The constant movement of air across exposed ridges influences how bark forms and hardens. Wind can shape bark texture. Trees growing in windy areas may develop denser wood and slightly altered bark patterns due to the stress placed on the trunk. Repeated mechanical pressure from wind encourages stronger structural growth beneath the bark. The outer layers respond by forming ridges that align with the trunk's expansion. In coastal environments, salt spray affects bark as well. Some species develop bark that resists salt damage, preventing dehydration of the outer cells. Even rainfall patterns influence bark. In tropical rainforests, where humidity is high and moisture is constant, bark may remain thinner and smoother in some species. Thick, deeply furrowed bark is less necessary when fire is rare and temperature swings are mild. However, high humidity increases fungal pressure, so chemical defenses within bark become important. The structure of bark is always a compromise. It must protect against insects, fungi, temperature shifts, and physical damage. But it must also allow the tree to grow without using too much energy, building unnecessary thickness. You can picture trees across different landscapes. In the desert, trunks stand beneath wide, cloudless skies. Bark reflects light or stores water carefully. On mountain slopes, wind moves steadily across rough surfaces. In northern forests, bark endures long, quiet winters. In humid tropics, smooth bark sheds water and resists decay. Each trunk carries the shape of its environment. Climate does not change bark overnight. It shapes generations slowly. Trees that survive harsh sun pass on traits that manage heat. Trees that endure cold pass on traits that buffer freezing. The cambium beneath continues its steady outward growth in all of these climates. But the layers it produces are influenced by temperature, moisture, wind, and light. Even within one species, bark may vary slightly depending on where it grows. A pine on a dry hillside may develop thicker bark than one growing in a sheltered valley. Local conditions leave subtle marks. If you move your hand from the smooth trunk of a desert tree to the ridged bark of a mountain pine, you are feeling adaptation in physical form. No bark is accidental. It reflects pressure applied slowly over time. Heat, cold, dryness, wind, shaping the outer layer that stands between life inside and the climate outside. And as environments shift, bark continues adjusting quietly, layer by layer, responding to the air, the light, and the temperature that surround it each day. If you stand in a mixed forest and look from one trunk to another, you will notice that bark does not follow one design. Some surfaces are smooth and pale. Others are dark and deeply furrowed. Some peel in thin curls. Others form thick plates that lift slightly at the edges. The differences are not small. They are distinct enough that foresters often identify trees by bark alone, even in winter when leaves are gone. Birch trees are among the easiest to recognize. Their bark is thin, pale, and papery. In many species, it appears white, though some are yellow or silver. The outer layer peels in horizontal strips. This peeling happens because the bark forms in thin sheets that separate easily as the trunk expands. The pale color reflects sunlight, reducing heat absorption. The surface contains oils and compounds like betulin, which give birch bark its distinctive brightness and help resist moisture. If you gently lift a loose strip of birch bark, you will find multiple thin layers beneath it, each formed as the tree widened. Oak bark, by contrast, is heavy and deeply ridged. On mature oaks, the surface forms thick vertical furrows that can feel almost rugged under the hand. These furrows develop as the trunk grows steadily over many decades. The outer bark becomes corky and dense. The deep cracks create shelter for insects and small organisms. Oak bark is especially rich in tannins, which help resist fungal decay and insect damage. The texture of an oak trunk often grows more pronounced with age. Young oaks may appear relatively smooth. Over time, ridges deepen and plates widen. Pine bark offers yet another pattern. Many pine species develop bark that forms large plates. These plates may be orange-brown, grey, or reddish, depending on the species. In some pines, the plates are thick and block-like. In others, they are thinner and more flaky. As pine trees mature, their bark thickens significantly, especially in fire-prone regions. The outer layers become rough and fibrous, helping to insulate the trunk. If you look closely at pine bark, you may notice resin beads where small injuries occurred. Resin flows from canals within the wood and hardens at the surface. The pattern of pine bark often changes as the tree ages. Lower sections may develop thicker plates, while upper sections remain smoother for longer periods. Sequoia bark stands apart. It is fibrous and deeply furrowed, often reddish-brown in color. The texture feels almost soft compared to other thick barks because it contains many air-filled fibers. These fibers make the bark lightweight despite its thickness. In giant sequoias, bark can exceed 12 inches deep. The fibrous quality contributes to fire resistance. It slows heat transfer and allows the trunk to endure repeated low-intensity burns. Unlike birch, sequoia bark does not peel in thin sheets. It remains attached, building up in layers over centuries. Each of these bark types reflects a different balance of needs. Birch prioritizes light reflection and shedding. Oak builds dense protection. Pine forms plated armor with resin support. Sequoia grows fibrous insulation. You can picture walking through a forest and noticing these textures in sequence. Smooth, pale trunks catching light. Dark, ridged trunks absorbing shadow. Reddish, fibrous surfaces rising straight upward. Even without leaves, the forest carries identity in its bark. The patterns are consistent enough that botanists rely on them for classification. In winter, when branches are bare, bark becomes one of the primary visual clues for identifying species. The color, depth of furrows, presence of peeling, and arrangement of plates all provide information. Bark is not uniform even within a single tree. Near the base of a trunk, bark may be thicker and more deeply ridged. Higher up, where the trunk narrows, it may remain smoother. Younger branches often have thin bark compared to the main trunk. These variations tell a story of age and exposure. As the cambium produces new layers year after year, the outward surface shifts in response to species genetics and environmental pressure. The outer bark thickens, cracks, or peels according to its inherited design. If you press your palm against birch, oak, pine, and sequoia in turn, you would feel 4 very different surfaces. Smooth paper, deep grooves, layered plates, fibrous ridges. Yet beneath each one, the same narrow cambium continues its steady outward work. The surface may differ, the process beneath remains the same. Layer forming under layer. Protection shaped by species. Texture shaped by time. And in those visible differences, the forest reveals its quiet diversity, trunk by trunk. If you have ever sprinkled cinnamon onto warm food, you may not have thought about where it began. Cinnamon is bark. More specifically, it comes from the inner bark of certain trees in the genus Cinnamomum. These trees grow in warm climates, often in parts of Sri Lanka, Indonesia, and other tropical regions. The spice that smells sweet and earthy once formed part of a living trunk, carrying nutrients through narrow channels beneath the surface. To harvest cinnamon, workers first cut young stems from the tree. The outer bark is carefully scraped away. This outer layer is protective and dry. It is not the part used for spice. Beneath it lies the inner bark, the phloem, the same nutrient-carrying tissue we have discussed in earlier sections. The inner bark is softer and more flexible. It contains compounds that give cinnamon its familiar aroma and flavor. Once exposed, this inner layer is gently loosened and peeled away in long strips. As these strips dry, something interesting happens. They begin to curl. The curling occurs because the inner bark shrinks unevenly as moisture leaves it. The outer side dries more quickly than the inner side. This difference in drying speed causes the strip to roll inward, forming the small quills often seen in stores. What looks like a carefully shaped stick is simply bark responding to air. The process is quiet and gradual. Freshly harvested strips lie flat at first. As hours pass, they begin to curve. Over days, they harden into the familiar shape. Harvesting cinnamon does not require cutting down the entire tree. In many cases, farmers manage the trees by allowing them to regrow stems after cutting. The cambium beneath the harvested area continues producing new layers. Over time, new inner bark forms. Because the inner bark carries sugars from leaves to roots, removing it in a complete ring around a mature trunk would damage the tree. But harvesting from younger stems or controlled sections allows regrowth without killing the plant. The tree continues its slow outward expansion. Within the inner bark are specialized cells that transport nutrients downward. These cells form a delicate network beneath the protective outer layer. When harvested carefully, only part of this network is removed. The remaining cambium and surrounding tissue continue their work. Cinnamon's warmth in scent and taste comes from compounds stored within these inner bark cells. Cinnamaldehyde is one of the primary molecules responsible for its characteristic aroma. These compounds evolved as part of the tree's natural chemistry, possibly serving as defense against insects or fungi. Humans discovered that these same compounds were pleasant in food. The idea that a common kitchen spice began as nutrient-carrying tissue within a living trunk may feel surprising. Yet it reflects how bark is more than surface protection. It is layered, functional, and sometimes aromatic. As the tree regrows, new bark forms outward from the cambium. The outer layers dry and harden. Beneath them, fresh inner bark develops. The cycle repeats quietly. In plantations where cinnamon is cultivated, harvesting happens at intervals that allow recovery. Stems are cut, bark is removed, and new shoots rise from the base. The plant remains rooted, drawing water upward and sending sugars downward. When you hold a cinnamon stick, you are holding a record of that process. a strip of inner bark, once flexible and alive, now dried and curled. It carries the memory of growth rings forming beneath it, of cambium dividing, of outer bark protecting, while inner bark transported nutrients. The spice does not look like armor. It does not resemble thick sequoia bark or furrowed oak plates. Yet it began within the same layered system. Bark can insulate against fire. It can shed in papery sheets. It can curl into fragrant quills. And in other trees, it can form something entirely different. There are forests where the outer bark itself is harvested, not for flavor, but for its structure. A bark that can be removed again and again without ending the life of the tree. That bark is cork. In parts of Portugal and Spain, there are forests where bark is harvested in wide, curved sheets. The trees remain standing. These are cork oak trees, and their outer bark is one of the few types in the world that can be removed again and again without killing the tree. Unlike cinnamon, which comes from inner bark, cork comes from the outer bark. The thick protective layer that forms as older tissue is pushed outward. When a cork oak reaches about 20 to 25 years of age, its bark becomes thick enough to harvest. Workers use special axes to carefully cut vertical and horizontal lines into the outer bark. They do not cut deeply into the living cambium beneath. Instead, they loosen the thick cork layer and peel it away in large curved panels. The trunk beneath looks smooth and reddish after harvesting. The tree is not harmed if the inner layers remain intact. Over time, the cambium continues producing new outer bark. The cork layer slowly rebuilds. After about 9 to 12 years, the bark becomes thick enough to harvest again. This cycle can continue for over a century. Some cork oaks have been harvested many times in their lifetime. Cork cells are unique. They are filled with tiny air pockets. Each cell is like a miniature sealed chamber containing gas. These air-filled spaces make cork lightweight and compressible. When pressed, cork can bend and then return to its original shape. This flexibility makes it useful for bottle stoppers, flooring, and insulation. Because cork contains suberin, the same waxy substance found in other bark types, it resists water and decay. It does not absorb moisture easily. It also resists fire. The air pockets within cork slow heat transfer, much like the fibrous bark of fire-resistant trees. When a cork oak is harvested, the outer bark that has served as armor becomes a renewable resource. The careful cutting process is important. If workers cut too deeply and damage the cambium in a complete circle, the tree could be harmed. But skilled harvesters know how to separate the cork layer without interrupting the living tissue beneath. After harvest, the tree stands quietly in the sun, its trunk exposed in a reddish tone that gradually darkens over time. New bark begins forming almost immediately. The regrowth is slow. Layer by layer, the outer surface thickens. The cambium continues dividing. The tree does not rush the process. Cork oak forests are considered valuable ecosystems. Because the trees are not cut down during harvesting, the landscape remains intact. Birds, insects, and mammals continue to live among the trunks. The cycle of removal and regrowth becomes part of the forest rhythm. The harvested cork sheets are stacked and left to dry. Later, they are boiled to remove impurities and increase flexibility. The material is then shaped for various uses. When you hold a cork stopper, you are holding bark that once wrapped around a living trunk. It protected against insects. It slowed moisture loss. It absorbed heat. And after removal, the tree simply began building it again. This regenerative quality is rare. Most trees would not survive repeated bark removal. But cork oak evolved with thick outer bark that separates cleanly from the inner living layers. The boundary between outer cork and inner phloem is distinct enough to allow careful harvesting. The presence of air pockets also explains why cork floats. Its density is lower than water. The same structure that insulates against heat makes it buoyant. Over decades, cork oaks grow wide and sturdy. Their bark becomes deeply textured. Each harvest leaves subtle marks on the trunk, but the tree continues expanding outward. You can imagine the forest standing under a clear sky. Some trunks dark and textured. Others recently harvested, glowing softly in red tones. Beneath the surface, cambium rings continue their steady outward growth. The outer bark that once acted as armor becomes something else in human hands. Yet the tree remains rooted, layer forming under layer, protection rebuilding slowly. Cork shows that bark is not only a shield, it can also be renewable. It can be removed and returned. It can serve both the tree and the wider world without ending its life. And while cork oak forests stand quietly through the seasons, their bark supports more than human use. The surface of bark, whether corky, fibrous, or deeply ridged, becomes home to small worlds. Moss gathers in shaded cracks. Lichen spreads across pale surfaces. Insects move along hidden channels. Even the armor of a tree carries life upon it. If you look closely at a tree trunk, you may notice that the bark is rarely bare. Small patches of grey, pale green, or soft yellow may cling to the surface. In shaded areas, tiny cushions of moss may gather along grooves. Within cracks and furrows, insects move quietly, often unseen. Bark is not only protection for the tree, it is also a surface where small ecosystems form. Lichen is one of the most common life forms found on bark. It appears as crusty patches, leafy clusters, or delicate branching forms. Though it may look like a single plant, lichen is actually a partnership between fungi and algae. The fungus provides structure and protection. The algae, or sometimes cyanobacteria, produce energy through photosynthesis. Together, they create a living layer that rests on the bark's surface. Lichen does not draw nutrients from the tree itself. It absorbs moisture and minerals from rain, air, and dust. It uses bark simply as a stable place to grow. In this way, the tree supports life without being harmed by it. Different types of lichen prefer different bark textures. Smooth bark may host thin, crust-like lichens. Deeply furrowed bark may allow leafy or branching types to settle into cracks. The chemical makeup of bark also matters. Some species grow more easily on acidic bark. Others prefer more neutral surfaces. Moss often appears in areas where moisture lingers. Unlike lichen, moss is a small plant. It has tiny leaf-like structures and grows in soft green mats. Moss thrives in shaded areas where water remains on the surface for longer periods. The cracks and ridges of bark create small pockets where moisture can collect after rain. These damp spaces allow moss to anchor gently against the trunk. In humid forests, moss may climb several feet up a tree. In drier climates, it may appear only near the base, where water from soil and rain splash keeps the bark slightly damp. Insects also find shelter in bark. Beetles may hide beneath loose plates. Ants may travel along deep grooves. Tiny larvae may develop within narrow crevices. The texture of bark creates hiding places from predators and protection from wind. Spiders spin webs between ridges. Small moths rest against the surface, blending with the bark's pattern. Even birds use bark indirectly, searching its cracks for insects to feed their young. Each groove and ridge becomes part of a layered habitat. Bark texture influences which species gather there. Smooth trunks offer fewer hiding spaces, but may still support thin lichens. Rough trunks with deep furrows create more complex microhabitats. The thicker and more textured the bark, the greater the variety of small life it can host. Moisture, sunlight, and temperature all shape these tiny communities. On the north side of a tree in the northern hemisphere, where sunlight is less direct, moisture may linger longer. Moss and lichen often grow more heavily there. On the south-facing side, where sunlight warms the trunk more strongly, surfaces may remain drier, limiting growth. These differences can appear subtle, yet they create variation around a single trunk. The bark itself remains focused on its primary task of protection. It does not feed the lichen. It does not nurture the moss intentionally. But by offering texture, stability, and shelter, it supports life in quiet ways. Over time, layers of lichen may accumulate, giving bark a soft, patterned appearance. Moss may cushion the surface, especially near the roots. Small seeds carried by wind may settle briefly in moist cracks before falling away. Even in winter, when leaves have fallen and branches appear bare, bark continues to host these small worlds. If you lean close to a trunk, you might notice how still it seems from a distance, yet how active it becomes up close. Tiny movements, subtle color changes, a quiet community resting against the outer armor. These life forms do not weaken healthy bark significantly. In most cases, they coexist without harm. Their presence reflects stable air and moisture conditions. In fact, some lichens are sensitive to air pollution, making them indicators of environmental health. The bark stands between interior and exterior, and on its outermost layer, another layer of life settles. What appears rough and protective from afar becomes, up close, a landscape of miniature shapes and textures. Pale branching lichens spreading across ridges, moss collecting along damp grooves, insects moving within shadowed lines. The armor of the tree becomes ground for other organisms, and in that quiet layering of life upon protection, the forest grows more complex, not only in height and width, but in the small worlds resting gently on its surface. If you have ever stepped into a forest and noticed how the air feels quieter, part of that calm comes from bark. Forests do not silence sound completely. Birds call, leaves rustle, branches shift in wind. Yet compared to open fields or hard city surfaces, forests often feel softer to the ear. One reason for this softness is texture. Sound travels in waves. When those waves strike smooth, hard surfaces like concrete or glass, they reflect sharply. The sound bounces back in clear echoes. But when sound meets rough, uneven surfaces, the energy scatters. Bark is rarely smooth. Deep furrows, fibrous ridges, peeling layers, and corky plates all disrupt sound waves. Instead of reflecting in one direction, waves break apart across the irregular surface. Small pockets of air within bark absorb part of the vibration. The energy weakens as it spreads. Thick bark also reduces vibration traveling through the trunk itself. When wind pushes branches together, or when animals move through the forest, the trunk vibrates slightly. Dense wood fibers and layered bark dampen that motion. The vibration does not travel far. It fades quickly. This dampening effect contributes to the feeling of quiet. In a forest filled with rough bark trees, each trunk acts like a natural sound diffuser. Waves that might echo in open space are broken up by layered textures. The result is not silence, but softness. Imagine clapping your hands in a large empty hall. The echo lingers. Now imagine clapping in a forest clearing surrounded by trees. The sound fades more quickly. The difference lies in the surfaces that absorb and scatter the waves. The fibrous structure of bark helps with this process. Inside thick bark are small air-filled spaces. When sound waves enter these spaces, part of their energy is converted into slight movement of air and fibers. This movement reduces the intensity of the wave as it passes. Corky bark is especially effective at absorbing vibration. The same air pockets that make cork lightweight also interrupt sound transmission. Fibrous bark, like that of sequoias, behaves similarly. Even thin bark contributes to the effect through its uneven surface. Texture matters. Deep cracks create narrow channels that trap small amounts of sound energy. Raised ridges cast tiny acoustic shadows. No two surfaces are identical, so reflections become irregular and scattered. Leaves and forest floor materials also absorb sound. Fallen needles, moss, and soil dampen footsteps and wind movement. But bark plays a steady role year-round, even when leaves have fallen. In winter, when branches are bare, trunks remain. The forest may appear skeletal, yet the rough surfaces still break apart sound waves. The sense of quiet you feel in a forest is partly the result of these countless small interactions between sound and texture. Even rainfall sounds different against bark than against metal or pavement. Raindrops striking ridged bark produce muted tones. Water running down grooves moves quietly along the trunk. The forest does not amplify noise. It softens it. Bark also influences how sound moves between trees. When wind pushes through branches, vibrations transfer into trunks. The layered bark reduces how far those vibrations travel. Instead of creating long, ringing tones, the movement remains local and brief. You might picture yourself standing still among tall trunks. The air feels thick with stillness. Distant sounds seem less sharp. Nearby movements fade quickly. The quiet is not complete absence of sound. It is moderation. Each trunk, wrapped in textured bark, interrupts echoes. Each ridge, plate, and fiber weakens vibration slightly. Over time, this collective dampening shapes the forest's acoustic character. In places with smooth bark species, sound may travel differently than in forests dominated by deeply furrowed trunks. Texture density affects how quickly echoes fade. The forest becomes a layered acoustic space. Bark, built for protection against insects, heat, and moisture, also shapes how we hear the environment. Without intending to, it softens the air. And as evening settles and wind calms, the rough surfaces of countless trunks continue absorbing and scattering the remaining sound, leaving behind a gentler hush that feels steady and grounded. In that hush, the slow work beneath the bark continues, growth moving outward quietly, layers forming year after year. While above the surface, the forest rests in softened sound. If you look at a young tree, its bark often appears smooth. The surface may feel thin and flexible. The color may be even. Cracks are shallow or not yet visible. At this stage, the trunk has not widened very much. The outer bark has not been pushed outward for many seasons. It still rests close to the living cambium beneath. As the tree ages, that changes. Each growing season adds a new layer of wood inside the trunk and a new layer of inner bark just beneath the surface. Over time, older bark is pushed outward. It thickens. It dries. It begins to split. The transformation is gradual. In many species, the bark of a sapling looks entirely different from the bark of a mature tree. A young oak may have smooth grey bark. Decades later, the same species will develop deep furrows and heavy ridges. A young pine may appear relatively plain. With age, its bark forms thick plates. This shift reflects steady outward growth. As the cambium produces new layers year after year, pressure builds beneath the outer surface. The bark responds by cracking, peeling, or thickening, according to the species pattern. The deeper the furrows, the longer the trunk has been expanding. Deep ridges often indicate maturity. While bark thickness alone cannot tell you the exact age of a tree, it can offer clues. Older trees tend to have more complex textures. The cracks grow deeper. The plates become wider. The surface gains character. In some species, bark continues thickening throughout life. In others, it reaches a stable pattern after a certain age. Growth rates also change over time. Young trees often grow more quickly, producing wider annual rings. As they mature, growth slows. The layers added each year become thinner. This slowing influences bark formation. When growth slows, outward pressure decreases slightly. The pattern of cracking may become more stable. In older trees, bark may feel firm and well set, reflecting decades of gradual expansion. Age also affects the protective function of bark. Thicker bark often provides better insulation against heat and cold. It may offer stronger resistance to insects. It may store more structural carbon. In many ecosystems, mature trees with thick bark are more likely to survive low-intensity fires than younger trees. The bark becomes not only older, but more capable. Carbon storage is another quiet aspect of aging bark. Trees absorb carbon dioxide from the atmosphere during photosynthesis. Carbon becomes part of sugars. Those sugars become wood and bark. Over decades, thick bark stores carbon in solid form. Even though bark is only one part of the tree's mass, its contribution increases as it thickens. In long-lived species, bark may hold carbon for centuries. As outer bark ages, it also changes in color and texture. Some bark darkens with time. Exposure to sun, rain, and wind slowly alters its surface. Moss and lichen may gather in cracks, adding layers of texture. Older bark may feel more brittle at the surface. It may flake or peel more easily in certain species. Beneath that outermost layer, newer bark remains flexible. If you compare the bark near the base of a trunk to bark higher up, you may notice differences. Near the base, bark has been forming longer. It is thicker and more deeply furrowed. Higher up, where the trunk narrows, bark may be thinner and smoother. These variations reveal the passage of time. The tree does not replace its bark in a single cycle, except in species that shed in sheets. Instead, most trees accumulate layers gradually. The outermost surface represents older growth pushed outward. The inner bark beneath remains active. You can imagine standing beside an old tree and placing your hand against its trunk. The deep grooves beneath your fingers form slowly, shaped by decades of outward expansion. Each crack marks the release of tension built by growth. The bark becomes a visible sign of maturity. It carries the memory of seasons, storms, and steady sunlight. It thickens quietly. It strengthens over time. As growth slows in older trees, the cambium still adds new layers, though at a reduced pace. The outward movement continues, but more gently. The bark's texture may remain stable for long stretches. Age in a tree is not expressed in wrinkles of skin, but in ridges of bark. The smooth trunk of youth becomes furrowed with experience. And beneath that textured surface, carbon remains stored. Growth continues slowly, and the tree stands rooted, carrying years not only in its rings within, but in the changing armor without. When we think about trees and climate, we often think about leaves. But bark holds carbon too. Every year, as a tree absorbs carbon dioxide from the air, it uses sunlight to turn that carbon into sugars. Those sugars move through the inner bark and into growing tissues. Some of that carbon becomes wood, some becomes roots, and some becomes bark. Bark may seem like only a surface layer, but it is built from carbon captured from the atmosphere. As the cambium produces new layers of inner bark and wood, it locks carbon into solid form. The outer bark, once living tissue, gradually hardens and thickens. Even though the outermost layers are made of dead cells, they still contain carbon that was once part of atmospheric carbon dioxide. In thick-barked species, this storage adds up. A giant sequoia, with bark over a foot thick, stores carbon not only in its massive trunk, but also in its fibrous outer layers. An old oak, with deeply ridged bark, carries carbon in every corky plate and furrow. The longer a tree lives, the more carbon accumulates in its structure. Bark contributes quietly to this storage. When we picture a tree standing for decades or centuries, we are looking at carbon held in solid form. Each ring inside the trunk represents carbon absorbed in a specific year. Each outward layer of bark represents additional carbon added and preserved. Even when outer bark cracks or peels in small sections, most of it remains attached for long periods. The carbon stays within the tree's structure until bark eventually falls away, or the tree decomposes. Forests as a whole play a large role in regulating atmospheric carbon. Through photosynthesis, trees remove carbon dioxide from the air and store it in biomass. This includes leaves, branches, wood, roots, and bark. Thick bark increases the total amount of carbon stored above ground. In fire-adapted forests, bark thickness has an additional effect. When low-intensity fires pass through, thick bark protects the living interior, allowing the tree to survive. This means the carbon stored in the trunk and bark remains in place rather than being released immediately through combustion. If a tree survives fire because of its bark, the carbon remains locked in solid form. Over time, this resilience contributes to long-term carbon storage within the ecosystem. Even in species that shed bark, the process is gradual. Flakes or strips that fall to the forest floor decompose slowly. Some of that carbon returns to the soil, becoming part of underground systems. Some returns to the atmosphere. But during the years it remains attached to the trunk, it is stable. The thickness of bark often reflects both environmental pressure and age. Older trees with decades of outward growth hold more carbon simply because they have had more time to accumulate it. The bark thickens along with the wood. Each added layer stores a small amount of carbon. Over many years, these additions become significant. Climate, growth rate, and species all influence how much bark contributes to carbon storage. Fast-growing trees may add bark more quickly. Slow-growing species may build thicker layers over longer periods. You can imagine the forest as a quiet archive. Each trunk holding carbon in rings within and bark without. Each layer representing a year when carbon dioxide was drawn from the air and turned into structure. The bark does not announce this role. It stands as protection. It cracks, peels, or thickens according to species. It insulates, shields, and hosts small ecosystems. But within its fibers and corky cells, carbon remains stored. When sunlight touches the canopy and wind moves gently through branches, the slow exchange continues. Leaves absorb carbon dioxide. Sugars form. The cambium divides. New wood and bark take shape. Layer by layer, carbon becomes part of the trunk's outward form. The process is steady and patient. The bark thickens not only as armor, not only as insulation, but as a record of carbon captured and held. And as forests stand across valleys, mountains, deserts, and coasts, their trunks quietly carry this stored carbon, built outward from the cambium, year after year, forming ridges and plates that reflect both protection and accumulation. From smooth saplings to deeply furrowed giants, bark becomes one more place where time and atmosphere meet. A surface shaped by growth. A layer holding what once moved freely through the air. And beneath it, the cambium continues its slow outward work, adding one more thin ring of carbon to the living structure with each passing season. If you stand beside a tree long enough, you might begin to notice something subtle. It does not grow upward from its trunk, it grows outward. Height comes from the tips of branches and the leader at the top. But width, the thickening of the trunk, happens in a thin ring just beneath the bark. This ring, the cambium, divides slowly and steadily. Each growing season, it produces new wood on the inside and new inner bark on the outside. The change is small. So small that from one week to the next, or even from 1 year to the next, you would not see it happening. But it is constant, quiet, predictable. Old bark does not stretch to make room for this growth. It cannot. Instead, it is pushed outward. What was once close to the living center slowly moves farther away over time. The inner bark that carried sugars 5 or 10 years ago becomes part of the outer protective layer. As it moves outward, it changes. The cells dry, they harden. They fill with protective compounds like suberin. They lose their active role in transporting nutrients. Eventually, the outermost bark is no longer living tissue. It becomes armor, still useful, still protective, but no longer part of the tree's internal circulation. And beneath it, new layers continue forming. You can picture the trunk as expanding from within, like a slow ripple moving outward year after year. The cambium adds one thin layer at a time, a fraction of a millimeter, a quiet addition to both wood and bark. Growth is measured in millimeters, but over decades, those millimeters become inches. Over a century, they become feet. A sapling with smooth, flexible bark becomes a young tree with shallow cracks. A young tree becomes a mature trunk with deep furrows and thick plates. All of it happens because of steady outward growth from a ring only a few cells thick. The bark you touch today may have begun as inner bark long ago. At that time, it was soft and alive, carrying sugars from leaves down to roots. As new phloem formed beneath it, it moved outward. It dried. It thickened. It became part of the protective exterior. The outward journey continues as long as the tree lives. Nothing inside the trunk leaps forward in sudden bursts. The cambium adds cells in a circular band that wraps the entire trunk. This band is delicate. If it were removed in a complete ring, the tree could not survive. Yet when left intact, it quietly builds strength year after year. The surface responds gradually to this pressure. As new layers push outward, the outer bark begins to crack or peel, depending on the species. These cracks are not signs of weakness. They are signs of expansion. The surface yields just enough to accommodate the widening beneath. If you were to make a small, harmless mark on the bark of a young tree and return many years later, that mark would now sit farther from the center than before. It would also look older, perhaps deeper in a furrow, or surrounded by thicker ridges. Outward growth never reverses. The oldest bark is always farthest from the center. The newest bark lies just beneath the surface, still flexible, still alive. The cambium remains between wood and bark, always producing more. In some species, outer bark eventually loosens and falls away in flakes or strips. In others, it remains attached for decades, building thick layers. Even when pieces fall, the loss is gradual. Only tissue that has already completed its role separates. Beneath every outer layer, a new one is forming. This creates depth not only in wood rings inside the trunk, but in bark layers outside. The trunk becomes a stack of seasons, each layer representing a year when sunlight was turned into structure. Imagine the tree standing through winter frost, spring rain, summer heat, and autumn wind. Each season adds a thin line of growth. The bark slowly thickens, carrying the memory of earlier years outward. Time passes, and the trunk reflects it. The outward thickening does not call attention to itself. There is no sudden swelling, no visible shift from one day to the next. But across decades, the change is unmistakable. a slender trunk becomes wide enough that you cannot wrap both arms around it. Smooth bark becomes rugged. Thin surfaces become deeply ridged. The cambium continues its work in silence, adding one more layer to the tree's history with each growing season. Old bark moves outward and ages. New bark forms beneath it. And in that steady expansion, the tree records the passage of time, not in dramatic motion, but in patient accumulation. Layer upon layer, season upon season, always outward, always slow, always steady. As the years move forward, the surface grows more textured, more complex, more shaped by weather and growth. What began as a smooth young trunk becomes a landscape of ridges and grooves. And through it all, the widening continues quietly, a gentle reminder that growth does not always reach toward the sky. If you look closely at the bark of an older tree, you may begin to notice something deeper than texture. You may begin to notice time. Deep grooves do not form in a single season. Wide plates do not lift overnight. The surface you see on a mature trunk is the result of steady growth, shaped by weather, fire, injury, and sunlight across many years. Texture becomes a record. When a tree grows quickly in its early years, the outward pressure on the bark increases. Cracks may widen more rapidly. Furrows may deepen sooner. In slower growing years, the changes are more subtle. The pattern that forms reflects not only the species, but the pace of growth. A trunk that widened quickly during years of abundant rain may show broader ridges. A tree that endured drought may display tighter, more compact patterns. Fire scars remain visible long after the flames are gone. If a wildfire burned one side of a trunk decades ago, you may still see a darkened hollow or a curved scar along the bark. Over time, the cambium formed new layers around the wound, but it did not erase the event. Instead, it surrounded it. The scar becomes part of the texture. Lightning strikes leave their own signature. A vertical crack running from canopy to base may mark where electricity once traveled. Even after the bark has grown thicker around it, the path remains visible as a line of altered texture. Branch scars remain for decades as well. When a branch falls or breaks, the tree grows new tissue around the wound. The outline of that lost branch stays visible as a rounded or oval mark. As the trunk widens over time, the scar stretches outward, but its shape remains recognizable. You might run your hand along a trunk and feel a raised ridge that once marked the edge of a wound. Weather shapes bark too. In windy areas, repeated pressure can influence how the trunk thickens. The side-facing prevailing winds may develop slightly different texture. Sun exposure may cause one side to dry and crack differently than the other. Rain running down the trunk may carve subtle channels along existing grooves. Freeze-thaw cycles may widen small cracks into larger ones. No two trunks look identical. Even trees of the same species growing side by side develop unique patterns. Their exposure to light may differ. One may have endured a small fire. Another may have avoided it. One may have lost a branch in a storm. The other may have grown undisturbed. These differences accumulate slowly. Texture becomes personal. The bark of a tree standing alone in an open field may differ from that of the same species growing in a dense forest. sunlight strikes differently. Wind moves more freely. The environment leaves marks. Growth rate plays a role as well. When conditions are favorable, the cambium adds thicker layers. Outward pressure increases, cracks widen. In less favorable years, the expansion slows. The pattern tightens. Over decades, these variations create a surface that reflects both biology and circumstance. If you step back and look at a row of trunks, you may see similar colors and general shapes. But as you approach each one, the individuality becomes clear. One trunk may have deep vertical furrows. Another may show irregular plates. A third may carry multiple scars from long past events. The bark becomes a visible history, not written in ink, not carved deliberately, but formed through growth responding to time. Even subtle changes in temperature and moisture influence the surface. A tree that experienced repeated cold winters may show frost cracks. One that endured insect attack may have small resin scars along its bark. The surface does not hide these events. It absorbs them. It grows around them. It carries them forward as new layers form beneath. You can imagine placing your palm against an old trunk and feeling the rise and fall of ridges beneath your fingers. Each ridge represents years of outward thickening. Each scar reflects a moment that passed and was incorporated into the structure. Time does not pass over a tree unnoticed. It passes through it. It becomes part of its surface. And in the deep grooves and textured plates, you can see endurance written quietly, not as dramatic change, but as accumulated response. Layered growth, weathered surface, individual pattern. A trunk shaped by years that remain visible long after the seasons that formed them have gone. A tree does not step away from danger. It does not lean aside when heat rises. It does not retreat when insects arrive. It does not move when wind presses hard against its trunk. It remains where it rooted. Because it cannot relocate, protection must be built into its structure. That protection is layered, and much of it begins with bark. When wind throws debris against the trunk, the outer bark absorbs the impact. Twigs strike. Small branches brush across the surface. The rough exterior takes the first contact. Beneath it, the cambium remains protected. When insects crawl along the trunk searching for entry, they encounter hardened tissue. Thick bark slows their progress. Resin may flow if small openings appear. The outer layers sacrifice small sections to prevent deeper damage. When sunlight heats the surface, bark absorbs or reflects the energy depending on its color and thickness. It slows the movement of that heat toward living cells. The outer layers may warm significantly, but beneath them, temperatures change more gradually. When cold air settles overnight, bark slows the release of internal warmth. The outermost cells may freeze. The inner layers remain buffered. This is endurance without movement. The tree stands in one place through storms, drought, and heat waves. It does not respond by fleeing. It responds by absorbing. Outer bark is the first to meet the world. If fire passes through a forest, the outer layers may char. The surface blackens. Some bark may crack or fall away. But if the cambium beneath survives, the tree continues. The outer layer sacrifices itself to protect what lies inside. If a branch tears away during a storm, bark around the wound may split. The exposed wood is vulnerable for a time. Yet the tree begins forming new tissue along the edges. The outer bark protects the area, while inner growth surrounds it. Strength comes not from hardness alone, but from layering. A single thin surface would fail quickly under repeated stress. But layered bark distributes force. Cracks in the outer layer do not necessarily reach the inner living tissue. Plates overlap. Fibers interlock. Air pockets slow heat. You can imagine the trunk as a standing column, wrapped in rings of protection. The cambium remains hidden just beneath the newest inner bark. It continues dividing, adding thin layers each year. Those layers push older bark outward. The surface thickens. The tree does not appear to change from one day to the next. Yet over time, the outer bark becomes more capable of absorbing damage. Endurance is quiet. It is not dramatic or sudden. It is built gradually, one growing season at a time. If you walk through a forest after a storm, you may see leaves scattered across the ground. Branches may have fallen, yet many trunks remain upright. Their bark may show small scratches or scars, but the structure holds. If insects burrow into one area, resin may bead along the bark surface. The damage may remain localized. The rest of the trunk continues its steady work of moving water and sugars. The tree does not resist by force. It resists by persistence. Outer bark may crack and flake. It may darken with age. It may carry scars. But beneath those layers, life continues. Even in harsh climates, where wind blows constantly or temperatures swing sharply, the trunk remains rooted. The bark faces outward in all directions, meeting each condition as it arrives. The outermost layers are always the first to encounter change. They weather, they dry, they thicken. They bear marks of past seasons, and the inner layers remain active. This is the quiet strength of a tree. It cannot move to safer ground, so it grows protection from within, layer after layer, season after season. The outer surface absorbs the world. The inner tissues continue their work unseen. And in that stillness, endurance becomes visible, not through motion, but through presence. A trunk standing year after year, bark facing outward, life continuing beneath it, steady and patient, while the outer layers meet each passing challenge and hold. If you return your attention to the surface of a tree, you may begin to see it differently now. Not as rough texture, not as background, but as the outer layer that protects life inside. Beneath the bark are the vascular systems that keep the tree alive. The xylem carries water upward from the roots. The phloem carries sugars downward from the leaves. Between them, the cambium divides and forms new growth. These tissues are delicate. They depend on steady conditions. Bark stands between those living systems and the outside world. It shields the phloem from insects that would feed on it. It slows fungi from reaching the cambium. It absorbs sunlight and moderates heat before it can move inward. It reduces moisture loss from the trunk. Without bark, the vascular systems would be exposed. Even small injuries could interrupt the movement of water or sugars. Even minor temperature swings could damage living cells. Bark holds the structure together in a quiet way. The outer layers support the trunk physically. Though most of the tree's strength comes from wood, bark adds resilience. It binds the surface. It cushions impacts. It distributes force across ridges and plates. In thick-barked species, the outer layer becomes substantial. It can be inches deep. It can insulate against wildfire. It can endure repeated seasons of freezing and thawing. In thinner bark species, the protection is lighter but still essential. Smooth bark may shed parasites. Light-colored bark may reflect heat. Even a thin outer layer is enough to separate living tissue from direct exposure. Each year, bark thickens slowly. The cambium produces new inner bark. The older inner bark becomes part of the outer protective layer. The outer bark may crack or peel as it moves outward, but beneath it, fresh layers continue forming. This steady thickening means that a tree's protection increases with age. A young sapling is more vulnerable. Its bark is thin. A small injury may reach the cambium more easily. As the tree matures, its bark grows thicker and more capable of absorbing stress. You can picture the trunk as wrapped in a living coat. The coat does not remain the same. It is replaced from within. The newest layer forms beneath the older one. The outermost surface carries marks of past seasons, while beneath it, new protection is developing. Life continues under that surface. Water rises through the xylem, pulled upward by evaporation in the leaves. Sugars move downward through the phloem, feeding roots and growing tissues. The cambium divides, adding another thin ring of wood and bark. All of this happens behind the shield. The bark may appear dry and silent. It may look cracked or peeling, but it stands between vulnerability and exposure. Insects crawl along its ridges. Rain runs down its grooves. Wind presses against it. Sunlight warms it. Cold air chills it. And still, beneath it, life moves. The bark does not announce its role. It does not change quickly or dramatically. It thickens slowly, year after year. It responds to injury by holding the boundary, while new tissue forms beneath. In some species, the outer layer becomes so thick that it feels almost like padding. In others, it remains smooth and tight. The form differs. The purpose remains consistent. Protection, structure, separation between inside and outside. If you lean your back against a tree trunk, you are resting against that protective layer. Beneath your shoulder blades, water is moving upward through vessels no wider than threads. Sugars are moving downward through living channels. Cells are dividing quietly in a thin ring. The bark absorbs the contact. It is the quiet surface that makes the rest possible. And as seasons continue to pass, the outer layer thickens a little more. The ridges deepen slightly. The plates widen gently. Life continues beneath it. Protected, layered, steady, held within a surface that faces the world so that the interior can remain alive and active, unseen and ongoing, year after year. As we come to the end of this quiet journey, you might see bark a little differently now. Not just as rough texture on the outside of a trunk, but as a layered system built slowly by the cambium. That thin, living ring just beneath the surface. The cambium divides each growing season, It forms new xylem inward, carrying water up from the roots. It forms new phloem outward, carrying sugars down from the leaves. And as those layers accumulate, older bark is pushed farther from the living center. What was once inner bark becomes outer bark. What was once soft and active becomes dry, protective, and strong. Over time, the outer bark thickens. It cracks as the trunk widens. It peels in birch. It forms plates in pine. It grows fibrous and fire-resistant in sequoia. It becomes cork in cork oak. It even becomes cinnamon in tropical groves, curled inner bark that once carried nutrients through a living stem. Through it all, bark serves as armor. It slows heat during wildfire. It buffers cold in winter and heat in summer. It resists insects and fungal entry. It seals small wounds with resin. It absorbs impact from wind and debris. When injury occurs, the tree does not heal like skin. Instead, it compartmentalizes. The cambium grows around damage. Scars remain visible. Time is written into texture. Deep furrows reflect decades of outward growth. Fire scars and lightning marks remain long after the event has passed. No two trunks are identical. Each one carries a record of seasons endured. And quietly, within every layer of bark and wood, carbon captured from the air remains stored. Year after year, sunlight becomes structure. The tree stands still. It does not move from danger. It builds protection from within. Layer under layer. Ring after ring. The outer bark faces the world. The vascular life beneath continues unseen. Water rising, sugars descending, cells dividing. If you imagine a forest now, perhaps you see more than trunks and branches. You see cambium working quietly beneath textured surfaces. You see old bark moving outward as new layers form beneath. You see armor shaped by climate, fire, wind, and time. Growth that happens slowly, outward, steady, unannounced. And as the image settles, a forest of trunks wrapped in layered protection, you can let your thoughts slow as well. No sudden changes, no urgency, just the quiet surface of time thickening gently, season by season, the outer layer steady, the inner life continuing. And with that steadiness in mind, you can allow the day to soften, layer by layer, breath by breath, rest arriving just as slowly and just as quietly.